Hey guys, this is Shelby with the Rochester Public Library. So this week for Full Steam Ahead, we're going to be talking about thermal radiation. So what is thermal radiation? Well, there's actually three ways that heat can move from one area to another. So if we're looking at a glass of hot water or tea or whatever, one way that the heat can move from the hot water to the surrounding environment is through convection. And that's where the water heats up the air right in this area, and now the air is less dense, so it rises, and then the cold air falls and it creates currents, right? So convection is heat transferred to currents. There's also conduction, which is when vibrating molecules send energy to the surrounding environment, right? So if the air that touches the sides of the cup as it warms up, that's conduction. The third way is radiation. And radiation is a little bit different in that it doesn't really involve molecules at all, or it does involve particles in a sense, but we'll get to that. So radiation. Okay, so think about this. You know that the sun is in the sky and the sun is very hot. You know that the sun takes heat to the earth, right? We get heat here on the earth, but space is a vacuum, right? There's not any air in space for the heat to transfer that way. So what's actually happening is that the heat that we get from the sun is in form of electromagnetic radiation. There's another name for electromagnetic radiation that you're more familiar with, and that's light. So light is a form of energy. It's a phenomenon related to electricity and magnetism. So we call it electromagnetic radiation. And light travels in waves. So you know what a wave is. If you've ever been to a beach, you've seen them in water at least. It's an oscillation, you could say, right? It's a motion that travels through without actually causing the water to move, right? There's a wave that goes through the water, but the water doesn't move. And that's kind of how light moves. The difference being that light doesn't need a medium. It travels through vacuums, whereas water waves can only travel in water. So how do we know that light is a wave? Well, there's actually a really cool experiment that I can show you guys, and this is called the double slit experiment. And it was first done about 300 years ago. And what you need is you need a wall, and you need an object with two slits in it, and you need a light. So I'm going to be putting the two slits over this. And if light traveled in a straight line, we'd expect to see just two slits in the wall. But we don't. We see this weird pattern where there's bright areas and there's less bright areas, and then there's areas where there's no lights at all. So this is caused by interference, and that's when the waves bounce into each other, and parts of the waves cancel each other out, and parts of the waves amplify each other. And so we get this scattering, right? So this is the proof that light is a wave. So some other things to know about light. So, well, this sounds kind of silly, but light travels at the speed of light, right? Light travels at the speed of light, right? Or all forms of light travel at the speed of light. So when we're talking about how much energy a wave on water has, we have to take in mind how fast it's traveling. We also need to take in mind how steep the curves or its oscillations are, right? But we don't do that with light. All light is at the same speed. So we say that light that has more energy has a shorter wavelength. That means it oscillates more times per second or per nanosecond, or however you want to measure it. And just so you know, the speed of light is about 300,000 meters per second, which is like a lot. Like, light can travel all the way around the Earth in less than a second. So for most purposes, when we say light is pretty much as an mind-bogglingly large enough speed that we think about it as being instantaneous. We don't have to worry about the actual time that light travels for when we're talking about stuff in the sky. So this, in terms of wavelength, when we talk about wavelength, we measure it in nanometers. So that's billionths of a meter. And this is the visual light spectrum. So from about 400 nanometers to 700 nanometers, that's what we see with our eyes. The shortest is violet light and the longest is red light. But there's also light with shorter wavelengths and longer wavelengths that we don't see, that's invisible, but it's the same phenomenon. So really short, really energetic waves or electromagnetic radiation is called ultraviolet light, X-ray, and gamma ray. And gamma ray is the shortest wavelength of all. And then on the longer wavelengths, we have infrared light, microwave, and radio wave. And radio wave is the longest. And the actual waves in radio waves can be like kilometers long, whereas over on this end we're talking about nanometers. So there's a big difference there. So the next question is, what is light made out of, right? You know, this travels in waves, and light is a wave, but light is also a particle. This is what I was talking about earlier. We said there is particles along here. So light is made up of photons, and you can think of a photon as being the smallest quantity of energy that's possible to exist in the universe. And we know about photons primarily because of someone named Max Planck, who's a German physicist, and Albert Einstein, who's another German physicist that you're probably familiar with. And they investigated some really weird stuff that happens with light. It's really complicated, but if you want to know more about that, here are some really good books. This is Mysteries of the Universe. Light, it specifically talks about the photoelectric effect, which is what Albert Einstein was studying when he came up with the idea of photons. And then this book is more general. It's called String Theory. So it talks about photons, and then it also talks about new ideas that physicists have thought of since they came up with the idea of photons. But, so, that's the lowdown on light. And now we're going to move into our experiment. And what you'll need for this is 2 mason jars and a little bit of paint and a thermometer. So these 2 mason jars, I painted one of them white and I painted one of them black. And so for our experimental setup, what we're going to do is we're going to take, if you have a mason jar lid, that's probably easier than this, but you can also just cover them with cups like this. And so now we have, these cups are insulators, so it's reducing the amount of convection that will heat up the water. And that means that the main difference between these two is the amount of thermal radiation that they absorb, and will cause them to heat up. So you take these and you leave them outside in the sun, and over time what you'll notice is that this cup, the black cup, gets hotter faster than the white cup. And that's because the black cup is better at absorbing photons than the white cup is. When something is black, it's because all of it absorbs electromagnetic radiation across the spectrum. Whereas this is white stuff is bad at absorbing photons, and so they all bounce off and it appears white to us. Or you can say photons across the spectrum, when they're all mixed together, appear as white. So we're seeing more photons bounce off, and we're not seeing any photons, or very few photons, bounce off of this. So it looks darker, and it also absorbs more energy from the photons and heats up faster. And you can actually do this in reverse, where you can put hot water in these 2 cups, and this one will cool down faster than this one, because things that are good at absorbing photons are also good at emitting them. And that has to do with the atomic properties of atoms and photons and electrons. Yeah, so it's a pretty cool experiment. Pretty easy to do. Although your parents might get mad if you paint dinnerware without asking them first, so ask for permission first. Our craft for this week is a little bit more involved. We're going to be using thermal radiation to melt crowns and produce some really cool melted artwork. So this is what I made. And how I did this was I crushed up some old crowns. You know, they were broken or they had lost their paper sleeves. So here is some black and blue crown, and you don't have to crush them up to the same size. These are a little bit bigger pieces, and these are really big pieces. So what you'll need is some construction paper and a piece of cardboard. It'll melt faster if you put aluminum foil on the cardboard, but you don't have to. You can also just do this. And I've taped the piece of paper down because when wax melts, it actually expands, and so and then when it cools down, it'll shrink again, and so it can kind of cause a warping effect like you see here. So if we tape down the edges, we'll stop that from happening. But you'll just want to put some crown on here. Try to make some cool pictures. Like this. You don't have to make any particular shapes. Let's see if I can get these and try to arrange it into a kind of flower shape. Okay, so you can do cool stuff like this. Say we have a flower and a flower stem. And then, what are we going to do next? We're going to take a glass pan, and it needs to be glass, and we're going to set it on top of it. And then you can just take your setup and leave it outside in the sun, or you can put it in a car on a sunny day. It'll work a little bit faster. But what happens with this is, when you have a mirror, it reflects light back at us, right? So we can see pictures of ourselves or images of ourselves. Glass actually works kind of similar to a mirror. The difference is that glass specifically reflects infrared radiation. So remember, that's infrared radiation is radiation that's past the visible spectrum. And so when light from the sun comes through the glass, it gets absorbed by all the objects in here. And then some of the light gets emitted as infrared radiation that we can't see. But that radiation gets stuck on the glass and bounces back in, and it creates kind of a greenhouse effect. And yeah, so you'll get a really cool melting effect with this. Although if you need to be careful and make sure you don't leave it for too long, or it might melt a little bit too much. That happened to me. There were more distinct shapes, and then they kind of bled together because I left it in the sun for too long. So yeah, that's our craft for today. Hope you guys had fun. I'll see you next time.